Perhaps we ought to start. Good morning. The topic I want to address today is multifunctionality in catalysts. That is the presence of more than one type of active site in a catalyst so that more than one basic type of reaction can occur. Now, in a way, this sort of behaviour will be familiar to you if you consider that if you have more than one sort of site and hence more than one sort of reaction, it may be possible for this to simply generate two competing parallel reaction pathways starting from a single reactant. And that would be the phenomenon that I think you would have probably met in the past. And it's not uncommon in catalysis to have some sort of parasitic reaction accompanying the main reaction. And generally speaking, an undesirable situation in the sense that the parasitic reaction will be competing for the reactant and will be diverting reactant away from the desired product. Just to give you an example of the sort of thing I've got in mind, you might imagine you had a nickel on silica alumina catalyst, which is in fact an article of commerce, which if used with, say, a mixture of olefin and hydrogen at a moderate temperature, perhaps 100 centigrade, you would expect to generate two reactions. On the nickel, you might simply get olefin hydrogenation and to the paraffin. And on the silica alumina, which has Bronsted acidity, in parallel with that, you might get the olefin undergoing double bond shift or skeletal isomerization. For instance, if the olefin in question was 1-butene, on the silica alumina you might be generating as products a mixture of say, 2-butene, double bond shift product, together with isobutene, the skeletal isomerization product. And provided the temperature is not too high, those two reactions, that is the formation of the paraffin on the nickel function and the formation of the other olefinic products on the acidic function, would operate independently, and they would only be coupled together to the extent that they were competing for the reactant 1-butene. That's a relatively, although it's not an uncommon situation, parasitic reactions are not uncommon, it's, from our present point of view, a relatively trivial example, and more important will be the behavior of multifunctional catalysts in which the reactions, the two reactions, which occur on the two active sites, occur sequentially rather than in parallel, in which case, for instance, the product of the first reaction becomes the reactant for the second process. And that's a much more sophisticated situation, because in fact the two cycles are coupled together via the intermediate product. The catalytic cycles are coupled together via the intermediate product. And of course the ability to form the end product at all is dependent on the interplay between the two processes. There are quite a number of these. I've got a few examples that I thought you might find interesting. Here's the first one I have for you. The conversion of an alkane, a paraffin, into isoalkane over a catalyst which, for instance, might consist of platinum dispersed on acidic alumina. The Cl in brackets here is to remind you that the acidity, the Bronsted acidity, or the acidity in general of alumina, is usually enhanced by by treatment with chlorine-containing compounds, and that increase in acid strength usually is thought to arise due to some sort of synergistic effect between chlorine bound to the surface of the alumina and neighbouring hydroxyl groups. However, you have two functions, the metallic platinum function and you have the acidic function on the alumina. And the conversion of the isomerization of the alkane then occurs by a sequence which is shown here, in which the steps are that the alkane is dehydrogenated to an olefin over the platinum function. The olefin, being as an intermediate product, is then transferred either by transfer through the gas phase or surface diffusion from the platinum function to a Bronsted acidic site on the alumina surface. At the Bronsted acidic site, the olefin will be protonated to form a carbenium ion. The carbenium ion then can rearrange to form say an isoolefin. And then the isoolefin is transferred back by the reverse of the mechanism which occurred in the first step of the reaction. That is, it is transferred back to the platinum site either by diffusion through the gas phase, desorption and reabsorption, or it's transferred back by surface diffusion to the platinum site, and then the isoolefin is hydrogenated at the platinum site to the isoalkane. In fact, an industrial process, or part of an industrial process. It's part of the catalytic reforming process. You might imagine that the extent to which these two sites could function in this synergistic effect, in this synergistic way, would be dependent to some extent on their proximity to one another. And while that is certainly true, if you can be sure that the transfer of material between the sites occurs by a surface diffusion process, which would clearly then would be favoured if the sites were close together. If the transport occurs through the gas phase, then that requirement for proximity of the sites is a good deal less important. And it happens in this case that while in practice one uses a catalyst in which the platinum function, the small platinum particles, in fact, are supported on the surface of the acidic alumina, which itself forms the second function, while that is the way in which the catalyst is generally prepared, you can in fact make this reaction go by taking two separate catalysts, one a platinum on an inert support, and physically mixing it with the acidic alumina, and that in that situation clearly the gas phase transport process is the one which transports the intermediate olefin and isoolefin between the sites. One other comment towards the bottom. It is known, and we mentioned this earlier in these lectures, it is known, of course, that platinum has several basic functionalities with respect to hydrocarbons. The platinum will function as a hydrogenation catalyst as well as a dehydrogenation catalyst, and this first step, alkane to olefin, which is a dehydrogenation step, will require the temperature to be fairly high so that you can get a tolerable equilibrium concentration of olefin in the dehydrogenation process. If that process is tried at a low temperature, the equilibrium concentration of olefin that you will produce out of dehydrogenation of an alkane will be miserable, so that you would tend to believe that you would have to run the reaction at a moderately high temperature, and in practice that's what's done. It's not uncommon for these things to run at 450 centigrade or even above that. And secondly, we note that platinum is a catalyst which will rupture carbon-carbon bonds in hydrocarbons. So hydrogenolysis would be a side reaction which one might have to do something about. And if you did decide that you wanted to suppress a parasitic hydrogenolysis process, you would refer back to the early lectures in this course where I dealt with the use of alloying with other elements to reduce the size of the surface ensembles that might be available for hydrogenolysis and hence suppress the hydrogenolysis process. Okay. I've got another one here which is related to that. Which is the conversion of alkanes to aromatics on a catalyst consisting of platinum dispersed on 8ZSM5 zeolite. Now I need to just give you a little bit of background about this. 8ZSM5, you remember, is a zeolite which is best known for its ability to convert methanol to aromatic hydrocarbons, and I referred to that in one of the previous lectures. And you will recall that the two basic steps which are involved in the conversion of methanol to aromatics are first the conversion of methanol to olefins. And the first olefins you will produce will be C2 and C3 olefins. Then there'll be an intermediate step in which these C2 and C3 olefins are oligomerized to higher olefins, particularly C6 to C8 olefins. And then these higher olefins are cyclized and dehydrogenated simultaneously to give you aromatics, particularly the xylenes out of C8 olefinic precursors. But for the present purpose, what I want to remind you of is the fact that ZSM5, in addition to having this ability to convert methanol to olefins, also has this ability with high selectivity to convert olefins to aromatics. And that leads you then to the notion that if you have a platinum 8ZSM5 bifunctional catalyst and you want to convert alkanes to aromatics, in rather the same way to the previous example, one can envisage a bifunctional catalyst in which the platinum acts as a dehydrogenating function to convert alkane to olefin. The olefin is transferred from the platinum site to the 8ZSM5 function and then undergoes, if necessary, an oligomerization process followed by a cyclization process to yield aromatics. And that can be readily done, and the only thing you have to again remember is that the platinum will be functioning as a hydrogenolysis site also, and you may, again, to repeat what I said before, one might have to do something to try and poison or otherwise remove those sites on the platinum surface which yielded the hydrogenolysis reaction. But that reaction can be done reasonably well. In fact, for reasons that are partly economic, that process is a quasi-commercial process. It's on the what I suppose I should say is teetering on the brink of commercial reality, because it offers a way of converting a gas like propane to aromatics, and the aromatics may well be required as a fuel blending agent. And if one started with propane, the sequence, which one would have to elaborate a little bit here, the sequence would be propane to propylene over the platinum function, dehydrogenation, propylene to higher olefins over the 8ZSM5 function by oligomerization, then cyclization and dehydrogenation also in the zeolite function. The same thing can be done with, instead of platinum, using gallium or zinc as a component in the ZSM5, and it also operates by functioning as a dehydrogenation site. It's not uncommon in catalytic cycles to have a requirement that an active site needs to be regenerated. And I don't just mean here regenerated from a poisoning process, although we will return to say something about that later on. But the active site may be converted to an inactive site as a consequence of the actual chemical transformation occurring in the catalytic process, or the quasi-catalytic process. The process then requires regeneration of the site before the cycle, the full catalytic cycle, can be established. And here I've got an example of this, which is based upon the so-called Wacker reaction, named after Mr. Wacker, who was a German, who, basing his work upon a small amount of previous work, and I'm now talking of the 1950s, I believe, devised a method for oxidizing ethylene to acetaldehyde, ultimately using oxygen from the air as an oxidizing agent. And the acetaldehyde at that time was a highly prized intermediate, because it could be then further oxidized by relatively conventional organic chemical means to acetic acid, and the Wacker process for making acetaldehyde for at least 2 decades was the basic route by means of which acetic acid was manufactured from ethylene, which was a cheap petrochemical source. Well, the chemistry is set out on this slide. The best way to approach it is to look at the basic step which tacks an oxygen onto the ethylene, and that's the first reaction here. It's done the reaction is done. The classical Wacker process is done in an aqueous system. It's a homogeneous process, and it was done using palladium 2+ in solution. However, the basic reaction consists of a water molecule yielding its oxygen to oxidize ethylene to acetaldehyde. The electrons from the oxygen are collected by the palladium, which is reduced to palladium naught, and 2 protons are generated. That's the basic oxygen transfer process. What's required, if that was all there was to it, that would be a simple stoichiometric reaction, and one would have to do something to reoxidize the palladium, which has functioned as a reducing agent, to oxidize the palladium back to palladium 2. What Wacker did, and that reaction, as that reaction written first was known, what Wacker did was to observe that it was possible to use the copper-2, copper-1 couple to oxidize palladium 0 to palladium 2, and then oxidize copper-1 back to copper-2 using gas phase oxygen. And here are the 2 reactions that I'm talking about written here. Palladium naught plus copper-2, it's a simple electron transfer. It's a simple ionic redox process. Palladium 2 and copper-1. And here's the key of the thing, in which copper-1 is oxidized by gas phase oxygen to yield copper-2, and you require 2 protons to balance the equation. And in fact, they're the 2 protons that are involved up here. Well, the Wacker reaction is all of that, and can be done in a one-phase system. That is to say, you can have palladium 2 plus copper ions in solution in water, in effect bubble oxygen and ethylene in and collect the acetaldehyde. It can also be done as sequential reaction in which you break these two things up into two components, and both of these approaches have been commercialized. If you regard, from our point of view, if you regard the palladium as the active site for the basic oxygen transfer process, what the bifunctionality of this reaction consists of combining the palladium function with the function depending upon the copper 1, copper 2 redox system for the regeneration of the basic palladium site which is involved in the oxygen transfer step. And as pointed out in the next sheet, you can in fact even heterogenize that Wacker process by, instead of working with copper ions in solution, you can work with copper ions that are exchanged into a zeolite, in which case the thing functions as a heterogeneous catalyst. And I was interested to read, when I got down to having a look at Gates's book on this, I was interested to see that relatively recent work shows that you can even get rid of the copper system completely and work with the vanadium 5+, vanadium 4+ redox pair as the method of regenerating the palladium function, but in an exactly analogous way to the copper function, except in this case I think yes, it uses V2O5, so it's also a function. It's also run as it's designed as a heterogeneous system. And Gates also points out that you can even use the quinone hydroquinone couple as the regenerating process in an analogous way. Gates's discussion of the Wacker process is worth having a look at. And I've got a couple more examples, but one more which shows as an example of the transfer of an intermediate. This is taken out of the recent literature, and this sheet plus the following one describe work done to make this dehydrogenation reaction possible. Conversion of 1-butene to butadiene by oxidative dehydrogenation. Butadiene's a highly prized petrochemical, and it goes, of course, ultimately into making things like maleic anhydride and polymers. It's been known for some time that that process can be done using a zinc ferrite, zinc spinel ferrite, which operates as a poor catalyst. And it basically appears to be a poor catalyst because if you're going to use molecular oxygen here, so that following the discussion we had previously on redox catalysts, what's really required to get going in a reaction involving gas phase oxygen is to adsorb the oxygen by an electron transfer process on the catalyst surface, which implies that you require variable valency in one of the metallic ions in the surface of the catalyst. It happens, although I guess you couldn't have predicted it, it happens that zinc ferrite, which contains iron 3, is almost totally irreducible, very difficult to reduce. And so that that being the case, that is to say, it's very difficult to generate Fe2+ in the surface of the zinc ferrite. It becomes very difficult to find sites upon which oxygen can be adsorbed by electron transfer, because you would expect the electron transfer process for the adsorption of oxygen as an ion of some description to require electrons to be transferred out of metallic ions which are situated in the surface of the catalyst, and the electrons are transferred to the oxygen. There must be some degree of reducibility of the iron in zinc ferrite to make this possible, but it appears to be a very poor function. On the other hand, it was known that it's possible, and there's it's well known for a long time that Fe2O3 is able to adsorb oxygen by electron transfer because Fe2O3 is readily reducible to contain Fe2 plus ions in the surface, and that's exactly what you might expect if you reflect upon the fact that Fe3O4, which is a stoichiometric material, of course, is a substance that can be prepared from Fe2O3 by partial reduction. And so it's not surprising, and Fe3O4 has Fe2 ions in it, so it's not surprising that Fe2O3 is reducible to the extent that one can generate a reasonably good concentration of oxygen adsorption sites. Now this, of course, this discussion begs the question of how, under catalytic conditions with oxygen being present, the Fe3 is reduced to Fe2 in order to get the reaction going. And if that worries you, reflect upon the fact that under all these conditions, you can easily generate some surface Fe2 ions by some sort of parasitic reaction with the hydrocarbon, which might go to CO2. And once you've got some Fe2 ions, they are retained as an integral part of the catalytic cycle. In other words, there will be a steady state concentration of Fe2 ions in the surface. Well, Fe2O3 adsorbs oxygen, but it has a relatively poor selectivity for the name reaction which you want to catalyze, mainly because the Fe2O3 tends to take the reaction right through to oxides of carbon. What was found was that if you have a bifunctional catalyst consisting of an intimate mixture of Fe2O3 and the zinc ferrite, you finish up with a catalyst that has both high activity and good selectivity for the desired process. And the implication then is, if you take these points together and think about what they mean for the way in which the reaction might go, you may come to the conclusion that the two sites operate by the Fe2O3 providing adsorbed oxygen, which takes part in the dehydrogenation process, and the zinc ferrite functions as a site upon which the 1-butene can be adsorbed. And so you come to the scheme which is on page 142B, which looks something like this. You're assuming you've got partly reduced Fe2O3 by some parasitic process. This provides Fe2 plus sites for oxygen adsorption, and here is the oxygen adsorption step, which is I've written out there to go from O2 minus right through to O minus, and I'm assuming that O minus is the active species in the dehydrogenation. That's an assumption. There's no justification for that other than hand-waving. And the proposition then is that you've got this, the basic catalytic cycle is as written here. Or that's not correct. The basic catalytic dehydrogenation process is as written here, in which on the surface of the zinc ferrite, an adsorbed oxygen interacts with adsorbed butene, pulls 2 hydrogens off. In the process of that, you've got to ditch the electron somewhere. There's an electron there to be got rid of, and it's got rid of by being transferred back to the Fe2O3 phase, which converts Fe3 plus to Fe2 plus. And the scheme then looks like this, as if you consider the two particles in contact, in which the oxygen's adsorbed on one site, the Fe2O3 site, or the Fe2 plus site. In the process of adsorption, it converts Fe2 to Fe3. It then assumes that by surface migration, the O minus ion is transferred to the other side, the other phase, and that it ultimately on this will encounter an adsorbed butene molecule, and the dehydrogenation step goes, and then you've got to get rid of the electron, which comes back onto the other particle. That is, in fact, as it was presented in the Journal of Catalysis. I would modify it to one extent. I think it is highly probable that the reaction which occurs on the zinc ferrite really occurs in this region here. That is to say that most of the zinc ferrite particle probably doesn't take part in the reaction, but you've got a small surface area adjacent to the point of contact between the particles, where a small distance over which the adsorbed oxide ion can migrate and react with adsorbed butene, and a small distance then for the electron to be transferred back into the Fe2O3 phase. I found that interesting. I hope you do. Here's a summary then of what you have to think about if you're going to try and design a catalyst to involve multifunctionality. Why do you do it? Well, you do it because you've come to the conclusion that the desired reaction overall, which you wish to catalyze, can only be done as the sum of more than one step. And you've come to the conclusion that the various steps involved require more than one sort of active site. So the first step is that you have a look at the reaction, overall reaction in question, and if necessary, break it up into contributing partial processes, and then try and assign some sort of optimum active site to each of these processes. And if you manage to get that far, you're well on the way. But it's absolutely essential to have a look at these contributing processes and see whether the sites that you've assigned are likely to be, in any sense, not mutually compatible. Will they destroy each other in some way chemically, by chemical interaction? And you also, and if your answer is yes, they are compatible, then you can conceive of the multifunctional catalyst operating in what I've called here a one black box conversion. That is, if you treat the catalyst in a black box, you can conceive of being able to run the reaction with reactant fed into one hole in the black box and product pouring out the other. On the other hand, if there is some degree of incompatibility, then you may have to consider running the reaction in a multi-black box, say a two-black box configuration, in which you take take step one with an intermediate product, assuming that it has enough stability to be isolable, to take the product out of as a product of step one and use it as a reactant for step two, and so on. So you need to look at the compatibility of what you've got. I tried to devise a bifunctional system which had never been thought of before. I've got one here which I'll discuss with you because it shows a little bit about how you might consider going about this sort of thing. It also shows problems that can occur, and I apologize, this is a somewhat complicated slide. It concerns the possibility of epoxidizing olefins by using oxygen as the epoxidizing oxidant. And this is what you really would like to do. You would like to take olefin, written there as CnH2n, react it with, in effect, half an oxygen molecule and form the epoxide. It's generally found that that sort of process is virtually impossible except in, or it is in fact virtually impossible. It's not uncommon, however, to make the compromise that you're prepared to split the oxygen into two bits, take one of the oxygen atoms and use it for the epoxidation process and ditch the second oxygen out of the O2. In which case you need an oxygen scavenger at the same time. And in other words, if you're using hydrogen, which is an expensive, I have to admit, an expensive scavenger, but never mind. If you use hydrogen as the scavenger for the second oxygen, then the stoichiometric reaction might be as written here. You see, what you're doing is you're taking, in effect, you're mentally splitting the O2 up into two oxygens. One of them's going on to the olefin to form the epoxide, and the second one is being scavenged to form water. And the fact that you're forming water would have some thermodynamic consequences because it would drive the reaction to the right, H2O being a stable molecule. Well, now, how are you to do that? You can't really hope to take a mixture of hydrogen and oxygen with an explosive mixture. But never mind, let's think about what to do. It invites you to think that you might be able to use hydrogen peroxide in place of H2 plus O2. And it turns out that hydrogen peroxide is a well-known oxidant, and provided you've got the right catalyst, will in fact epoxidize olefins. Here's the reaction here. I've written the catalyst as being this methyl rhenium oxide because this was I thought, a classy little catalyst which was reported in Allgemeine Chemie only about 2 months ago, but it appears to work quite nicely, and that's rhenium-7 and presumably functions as a redox catalyst involving rhenium-7 in a lower valence state. And so if let's assume that the report of that reaction is right, and that reaction can be made to go. What you have to do is think, here's what I need to really start with, hydrogen plus oxygen. How can I convert hydrogen plus oxygen to hydrogen peroxide? That requires another different catalytic function. Well, hydrogen peroxide is an article of commerce. How on earth do they make it? When you look that up, you might think, amazing, amazing. Here's how it's done. I kid you not, this is the industrial process. You take hydroquinone. Remember, hydroquinone is this. You take hydroquinone and treat it with oxygen. It's a non-catalytic process. It reacts with oxygen to form quinone, which is this. And hydrogen peroxide. And that process then, that's a stoichiometric reaction, and this is done, both of these are done as stoichiometric processes. The quinone, which I've called QO2, can be reduced catalytically using palladium metal to hydroquinone as a separate step. How can one combine those in some sort of total catalytic cycle which would generate the required reaction here? Well, you can't. I think the answer straight away is you can't hope to do it as a single catalytic process. You can't make that thing go, at least for one obvious reason, that you're very unlikely to be content to work with a feed mixture containing gas phase hydrogen and gas phase oxygen. So it's a two black box situation. In this case, the division into two black boxes in principle is required not because the sites are incompatible, but because two of the reactants are incompatible. And my suggestion is what you do is you take olefin plus oxygen plus hydroquinone plus the catalyst which is required to catalyze the epoxidation using the H2O2 as the reactive intermediate, And if one crosses one's fingers, one should be able to finish up with the epoxide, water, and the quinone, and then you have to cycle the quinone out of that process and reduce it as in black box number 2. And if you take the whole two together and cycle that thing back in here, taking the two together, you've got a closed cycle, but you've got 2 black boxes rather than 1 black box. I have no idea whether that works, and I'm only offering it to you as a sort of an illustrative way to think about the problem. When you look up, actually, you look up the, when you look up something about the generation of H2O2 using these reactions here, as a commercial process, you're told that it's a real black art. They use an incredible mixture of solvents in order to get the reaction to go optimally, and I hate to think of even attempting to actually do the work. It would be a good job for a graduate student. Let's leave bifunctionality and multifunctionality now and say something about poisoning and deactivation of catalysts, and we'll make a start today and continue and finish it in the first half of Friday's lecture. Poisoning and deactivation. What do they mean? Well, deactivation is usually just a general term which refers to the way in which the rate of a catalytic reaction is decreased during the course of the process due to, for instance, the reduction in the number of available catalytic sites, which might itself be due to poisoning, site poisoning. That is, the active sites may irreversibly adsorb a poison so that they become inactive. Or the catalyst may sinter in the sense that the total number of active sites decreases, for instance, due to surface area reduction. Or this deactivation might result from a decrease in the accessibility of the active sites. That is to say, if you have a porous catalyst, the pores may become physically blocked. And that can happen due to coking, for instance, which is typically a name given to a deposition of usually a high molecular weight polymeric material from hydrocarbon reactions, very common in acid catalyzed reactions. Due to coking or to fouling, and fouling is an industrial phrase which is usually reserved for a situation where you've got adventitious dust floating around in the gas stream, and the dust gets deposited on the catalyst and physically blocks the access of the reactant to the internal pores of the porous catalyst. Well, all of those go to form what is deactivation. Highly complex situation. It's usually treated on an empirical basis. But let's just give a few examples. Let's talk about site poisoning. We already had one example of that when we were talking about size shape selectivity. I pointed out that an acidic catalyst like HZSM5 can be poisoned by absorbing base molecules such as ammonia or organic amines at the Bronsted sites. That's one of them, but here are some more. Nitrogenous ligands may poison homogeneous metallic catalysts, and the typical example is pyridine, which will poison hydroformylation catalyst because the pyridine is strongly adsorbed at say the cobalt or the rhodium center, and once that's there it never comes off, and that's it. A couple of classic examples are with heterogeneous catalysts. Carbon monoxide is a poison for ammonia synthesis over iron catalyst. That goes back many years. Classical example. The carbon monoxide is strongly adsorbed, and in fact in industrial practice the folk go to considerable lengths to get rid of traces of carbon monoxide out of the nitrogen-hydrogen gas feed. Sulfur, for instance, present as H2S, is a poison for the conversion of carbon monoxide to methane over a nickel catalyst, mainly because the sulfur is strongly absorbed on the surface of the nickel. And finally, sulfur, again in the form of either H2S or simple organic molecules like mercaptans or thiophene, is a poison for catalytic reforming over catalysts such as platinum alumina or platinum rhenium alumina. Catalytic reforming, you remember, is the process, rather complex chemistry, but one in which you take alkanes and naphthenes, pass them at quite high temperatures over platinum alumina, and you get a complex series of reactions which involve partly, the catalyst is bifunctional, in which you convert them to aromatics and to isoalkanes and so on. However, it's sulfur poisoned, and again, the people who run these processes go to considerable trouble to get the sulfur levels down. It's particularly with these bimetallic catalysts like platinum rhenium or platinum iridium on alumina. It's not uncommon to avoid getting into a poisoning regime where the metallic function becomes inactive. It's not uncommon to require the sulfur levels to be in the few parts per million region, and that's a major hurdle when you're operating on a tons per day reactor basis. Well, having said that, that's the general impression is that poisoning is always bad news. Well, it's often bad news, but it's not necessarily quite so, always so. Here are a couple of examples where you can actually that you can make use of poisoning, and in both these cases it refers to sulfur poisoning. When you start up a catalytic reformer, which is one of these things I referred to just a few minutes ago, that is platinum alumina or platinum rhenium alumina or platinum iridium alumina, converting naphthenes and alkanes to aromatics and isomers, isoalkanes. It's not uncommon because of the metallic function has a hydrogenolysis function as well as a dehydrogenation function. It's not uncommon for the fresh catalyst to have an unsatisfactorily high level of hydrogenolysis activity. In other words, it forms a lot of methane and lower hydrocarbons, which from the point of view of the overall efficiency of the process are bad news. And to do something about that, it's standard practice in catalytic reforming management to use a very low level of sulfur in the feed to try and poison off the most active of the hydrogenolysis sites and quench the hydrogenolysis reaction. But it's tricky business, because if you go too far, you quench the dehydrogenation function too. However, it's done. And the other example I had here was, this is admittedly as a laboratory example, not an industrial example. In a study of the mechanism of carbon monoxide conversion to methane, the methanation of carbon monoxide on nickel, that's hydrogen plus carbon monoxide gives methane, it was shown, or use was made of the fact that the absorption of sulfur on the nickel surface removed, of course, nickel sites from being available for the reaction, and the way in which the kinetics of the reaction depended upon the concentration of sulfur on the surface enabled something to be said about the mechanism of the methanation process itself. In fact, I've given an indication here of what's involved. The rate of the methanation process goes as the square of the concentration of free sites, which in other words is 1 minus the concentration of poison sites squared. The fact that it's squared suggests anyway that the rate controlling step involves two free sites, and the fact that the reaction rate follows that law over quite a wide range of fractional coverage by poison, from 0 to at least 0.8, suggests that the reaction is insensitive. I think you need to put a... I'm not sure whether your copy has insensitive written there or sensitive. The reaction is insensitive. That is to say, it doesn't really matter what the surface plane is. All surface nickel atoms have about the same activity, provided they're not covered with sulfur poison. So, an example of the use of sulfur poisoning as a mechanistic diagnostic tool. I think we'll stop at that point. What I'm going to do on Friday is say something about sintering as a phenomenon, that's surface area loss, and then something about coking, and after that we'll go on to talk about catalysts as bulk materials. Regard to poisoning is that you need to remember, of course, that catalytic processes can be self-poisoned. That is to say, it's possible to have a situation where one of the products of a reaction is strongly adsorbed on the active site, in which case if that adsorption is irreversible, the active site may be destroyed by the initial product of the process, and there's nothing much you can do about it. That amounts to an extreme example of inhibition of the reaction by product adsorption. It's only a question of how strongly the stuff is absorbed. Let's move on and quickly say something about sintering of the catalyst. And sintering is can be talked about under two headings. One is generally, let me go back and start again. It amounts to a loss of surface area of the catalyst, and that can come about by either particle growth and or pore collapse if you happen to have a porous catalyst. Both of these processes, they may go on together or they may be separate. They generally result from transport of material under reaction conditions, and that transport can either be surface diffusion or, and in addition, it can be transport of matter through the vapor phase. A typical example, which I'm sure you must be familiar with, of sintering of finely divided catalysts is in finely divided metallic catalyst, which if used at high temperatures undergoes particle growth by surface diffusion. When the particles, if the metallic particles touch each other, then particle growth is a relatively facile process, and surface area reductions of a considerable magnitude are easy to achieve, which means a reduction in the total number of active sites and hence a reduction in the activity of the catalyst. Pore collapse is usually found in porous materials like aluminas or silicas, and it's particularly worth noting that sintering due to pore collapse is very often a function of the nature of the gas phase in contact with the solid, because and a particularly well-known example of this is the influence of water vapor on causing pore collapse in porous materials like silicas and aluminas and aluminosilicates. The sheet 146 points out to you that the loss of catalytic activity due to sintering may not be simply a matter of being proportional to surface area, because it's possible that if you have a structure-sensitive reaction, that is, one in which the catalytic activity depends upon the presence of special sites and hence upon, say, particle size or upon the presence of a particular crystallographic plane in the catalyst, then it may be possible for these special sites to be destroyed at a faster rate than the actual simple rate of reduction of total surface area, so that it's possible that under certain circumstances the sintering may result in a more rapid decrease in activity than just the surface area reduction would otherwise indicate. I've got one example on the next sheet which simply gives you an illustration of the style of thing that you may observe. It deals with dispersed platinum and alumina catalysts heated in air at a moderately high temperature, 973 K, and it shows the time dependence of the platinum dispersion being the ratio of the number of surface atoms in the platinum divided by the total number. In other words, it's a measure of particle size, if you like. And it shows you that the principal thing that it shows you is that the rate of platinum sintering depends upon the surface area of the support upon which the platinum particles are, over which the platinum particles are dispersed. And in effect that comes about because with a small surface area of the support, the platinum particles for a given mass ratio of platinum to support, the platinum particles are close together, and hence if surface diffusion or even if vapor transport was involved, it's much easier for sintering to occur when the particles are close together, that is to say when the support has a low specific area. And also that shows that in relatively unfavourable cases, particularly case B, where the support only had a specific surface of 6.6 metres squared per gram, the extent of reduction in the available surface area of the platinum over only a modest amount of time, 5 hours at sintering temperature, the extent of reduction in platinum surface area is very substantial indeed, and that catalyst would have presumably essentially died under those circumstances. Let's turn now finally to say something about coking. Generally speaking, when one talks about coking, one is talking about the deposition of high molecular weight carbonaceous deposits on the surface of the catalyst. And this results in a general inhibition of reactant access to the surface of the catalyst. It's mostly of greatest importance if with catalysts of an acidic nature, typically zeolites or silica aluminas, or any catalyst that has substantial Bronsted or in fact Lewis acidity. And it's the acidic nature of the catalyst which itself is responsible for the polymerization processes that produce the carbonaceous deposit on the surface. So it's in effect a self-fulfilling prophecy. As we'll show in a minute or two when I discuss, at least in one instance, some of the features of the coke-forming chemistry, coke formation can be influenced by size-shape selective properties of zeolites. And it's to some extent dependent on the acidic strength of the sites on the catalyst surface. The stronger the acidic sites, the more facile is the coke-forming reaction. And finally, and we'll return to this in a few minutes, there can be a synergistic effect in coke formation between the acidic sites and any metallic sites which might happen also to be present, and I'll explain how that can come about. And finally, just an obvious comment that provided the catalyst itself has sufficient thermal stability, you can remove coke by oxidation to carbon oxides by treatment with air or oxygen. It's usually referred to as burn-off, and in commercial practice, regeneration by oxidative burn-off of the coke is a standard procedure, and I'll say something a bit more about that too. The next sheet just gives you an example of the extent to which coke formation may occur under particularly favourable circumstances. And what it does is to show the rate of the time dependence of a cracking reaction on a rare earth exchanged zeolite, the time dependence of the rate of cracking of this C16 paraffin over a rare earth exchange zeolite, function of time. You might have a look at the ordinate on that graph. I took that, the graph comes out of the literature. I suggest, as I've done in the slide, in the sheet in front of you here, you cross out the word constant, because it's not a rate constant that's being plotted there, it's a rate. Okay? And the interesting thing is that the rate of the cracking reaction has fallen by more than a power of 10 inside 2 minutes contact time. So and that's entirely a result of coking. So it's a potent factor for change. It can be a potent factor for changing the activity of catalysts. And of course, in commercial operation, what is done is that they opt to live with this because they can't do anything about it. The catalyst is taken out of, in effect, taken out of use when it becomes appreciably deactivated. The burn-off procedure is applied to it, and then it's reintroduced into a reactor again, and that's the standard sort of technique in a fluid catalytic cracker, which is simply a way of the fluidized bed is a way of A, providing for intimate contact between the catalyst particles and the reactant gas stream, and B, it's a method of getting the catalyst to cycle between the reactor, where the cracking reaction occurs, and the regenerator, where the coke is burnt off. But the message is fast reaction. In that case, nothing can be done about it, and you design the process so that you live with the coke forming process. The next sheet says gives you some idea of size-shape selectivity effects in coke deposition on HZSM5, zeolite, and Y zeolite. This is really, it amounts to very little more than a redrawing of the diagram which I showed you in lecture before last, I think it was, concerned with formation of polymeric materials on zeolites when we talked about size-shape selectivity. But let's just go through it again here. All it says is that if you're starting with paraffins, the conversion of paraffins via olefins, via alkyl cyclopentadienes, to monocyclic alkyl aromatics and alkyl hydroaromatics, that sequence of reactions there, down to that point, can occur in the pores of HZSM5. In other words, all of these materials can be small enough to occur within the pores of HZSM5. However, to go beyond that point means that these things, particularly these alkyl hydroaromatics, have to migrate out of the pores. And if you want to get fused ring aromatics, particularly with 3 rings or more, that process then has to occur on the external surface of the HZSM5, and it's the continuation of this reaction which ultimately leads to the coke, which is a polycondensed aromatic structure of ill-defined composition. That implies, incidentally, that